Okay, so here we are. We're now doing Advanced Concept 6, and I'm extending this from my last video in the Core Concept series, which is on gravity and gravitation. But here I'm going to extend this thought more to a A-level exam perspective and just discuss how they want to tie that in with the application to problems that they could test you out in the exam. So let's get started with that. And I think I already have some of the stuff written down here on the board. Right, we'll start with the first one, which is the Newton's law of gravitation, and then I have a picture here illustrating that. We know all of this, we're not going to get into it too much, but we'll start with the first part, which is this equation got written as force is equal to, and then we created a universal gravitational constant, and we wrote the two masses, right, that we had, and the square of this distance between their center of mass. That really came from that, and g is the universal constant of gravitation. We have a value for it, so we're pretty comfortable with that part. We also said, in a case like this, where there is a larger x with respect to r, if r is now the radius of the Earth, so I'm going to bring this down to Earth, and I'm going to define just two values here just for the sake of computation. I'm going to use the term me for mass of the Earth, and I'm going to use re for radius of the Earth. And we could just say mean radius of the Earth, because the radius of the Earth is not necessarily identical across the entire sphere, and it's not even a perfect sphere, so but for the purpose of this, we're just going to say radius of the Earth, right? So we've got these two nailed out, and obviously my equation then would be written along the lines, and this doesn't change, right? This doesn't change. So I would effectively write this as mass of any particle, that's just a general m, times mass of the Earth, times. Now I'm going to write x, right? I'm going to write x as is, but if I were to bring the particle now, when x is equal to the radius of the Earth, we also know then the mass of the particle times acceleration due to gravity, and that would then equate to mg being equal to g times m times me by the square of the radius. We did this math and we figured out a relationship for g. Now I want you to just think about this for a second, and if you remember the proportionality and we made it into a constant, if you really think about this, the only variable here is this distance, because the mass of the two objects would fundamentally not change. Well, there are cases where it would change, like in the case of a rocket, which as it's firing and losing fuel, its mass reduces, and then obviously there is a greater equation there as relates to thrust and such areas. But for now, we are comfortable with this. We also developed a value for g, right? We would say we would be able to write the gravitational constant in terms of the mass of the Earth, right? So we know this. And if you knew the mass and the radius, you grew essentially a value, and if you wanted to establish this in terms of density of the Earth and volume, you could play with this a lot in many different ways. But what I want to get to is just extend this a little bit and think of this in terms of how problems can be set up. So if you just knew that an object of mass m, So in this case, and I'm continuing green because I'll stay with this idea. An object of mass m, right, would experience a force that is, if I wrote proportional to its distance from the, inversely proportional to its distance from the center of mass of the earth, and if I wrote that, you're with me so far, and I replace that with a constant of proportionality, saying that would be some constant. In this case, I'm just going to write k and write that with respect to the distance. I could, in theory, argue the case that I would say if my object was experiencing this acceleration due to gravity, this is the force that it's experiencing at, when it's placed in that special case, when it's right at that surface, I've written this much, right? On the surface, this is the force, right? This is the gravitational force when you're somewhere out there, but on the surface, the gravitational force is now written this way, which then leads me to write that K is equal to mg, radius of the Earth squared. If you're with me on that. If I take this and substitute this here into this equation, right? Let me just say at the surface for this, okay? Now if I substitute k back here, I could now, let me just say this is 1 becomes F is equal to mass times acceleration due to gravity times RE squared divided by x squared. And you can see as x tends to RE, you basically get just mg, because these two will begin to cancel out because x is getting closer to RE. So within reasonable distances to the surface of the Earth, this ratio becomes negligible. R is so large that adding a tiny bit to x over the R, because remember x is R plus something else, right? So when R is, say, 2,500 kilometers, adding a kilometer or 2 or 10 to 2,500 and then working the square out doesn't make much of a difference. And pretty much because RE is mean radius, so there are places where the radius is even higher than that. So the ratio doesn't significantly change. And for practical purposes, you would get forces equal to mg within the, proximity of the Earth's surface. This is an area this is something you should remember, because they could ask you with different variables and notations. A question could be posed that would ask you to prove this relationship, and this would be important, and they could give it to you in different ways. With this in mind, we're now going to go to a slight extension, and I have drawn out here a particle of mass m and at a distance d from the center of the Earth. This can be given to you as a distance d from the surface of the Earth, in which case you have to make sure you add that value in this equation. But what I want to just go and have you think about is, if I have an object and it's moving away from the Earth, like a rocket, that's usually the case. And if they give you a free fall problem, it's a little bit different. Usually they don't. When it comes to gravity, they tend to look at objects moving away. But if you did have a satellite that's falling free, the issue is because they don't really fall in a straight line and they tend to circle around, I don't think they'd mix it up with that, because you could develop a harmonic function as well, because you'd go around the Earth and loop back, and that's where the elliptical orbit shows up. And I don't think they'll get to that area, because I don't think that's the extent of mathematics you are learning. However, the fundamental concept that they want to look for is this, right? So here you have the object at some distance from the surface or some distance from the center of the Earth. What is going to happen there is you're going to write a force that the object experiences, which is that divided by, let's say, in this case, it's d squared, right? And why did I write that? Because I established this, right? The way I established this, I chose this constant. The reason I had this constant is really I had the g and the m in that constant, right? And then that's what I've equated. Now, if they could trick you without having to go through this, and then you might just get the mass of the Earth as a value, and then of course you would write the force really as, and if they gave you g, you could write that. If they didn't give you g, you could also substitute this g for the mass of the Earth into this equation. You'll effectively get something identical to what I've written, right? Sorry, this would be a square. So you basically, if you took this and substituted it into that into this, you'll basically get very similar results. So you have this force that's going in one direction, right? Or rather, this is pulling the object back, right? And let's say there is a forward force that's sending the rocket forward. In which case, assuming, and you'll do net forces really to arrive at it, but just getting this right, once the rocket's out into, it's out there and it's moving forward, all I'm doing is I've imparted enough velocity into it. All I'm doing is just having enough force come out of the thrusters such that I counter the force due to gravitation, right? Because I've already got velocity. I've reached a particular velocity. Now my thruster just needs to create enough force. I don't need to accelerate any further, right? If I assumed that to be the case, I could write this equation, and then if I take this to its generic form, right? This force has a mass times acceleration, right? And that's negative mass times re squared by d squared times another, so it's mass times this, so actually let me write it this way, times d squared, right? So it's mass times that. You with me? If the masses cancel out, I have an acceleration on one side, which is some constant, re and g, and then a d squared, which is basically a displacement value. So I have now created this equation, if you remember, and this is why I want to discuss this in the advanced area at this stage, because you've seen varying acceleration, you've seen motion, forces that vary with time, and how that is really just acceleration. You've seen harmonic motion as a special case, and I hope I can tie that to you, because you can see how these forces, if you were coming down in towards the Earth, how gravity would bring you, but then you'd move back and loop back and forth, and which is what causes the elliptical orbits. You have those ideas, but now here I can now write this as, what am I writing? It's negative some constant k lowercase by a displacement value. I hope you see that. And the reason why I have a negative is it's very easy. Its acceleration is working against the motion. Simple harmonic motion, remember that as well, right? When we pulled in, there was a direction of motion and acceleration is against it. You can see I'm getting the exact similar equation, and that's why you can derive this relationship that when you get pulled in with gravity, you just don't go knocking in, same application in a black hole. You don't just have particles going in, they seem to spin around, and that's really the harmonic nature that gives that spin. All of that stems from this fundamental motion relationship. So K, it's not R, it's a K. Should I write that? That's a K. I don't know if that's the nice way of writing K. I just messed it up. Right? So it's K. What happens here? If you remember, when we have an equation like this, we can also write V dV by dx is equal to negative K by x squared. If you know your integration, V squared by 2 is equal to a positive K by x. And you can work it out. You'll have a value for, you'll have the relationship or an equation of K or of some sort, and then you'll have X. And this is basically negative 1, right? So it'll be, yeah, minus 1. So that negative cancels this negative out, and V is just V squared by 2. Again, velocity as a function of displacement and time. I have displacement itself. I can reverse engineer the equation to also get a displacement as a function of, so this is basically dv by dx. Once I have a square root here, this is dv by dx. So 2k root, root of 2k and divide the root of x would be v, which is dv by dx. And if I then take the dx there, I can integrate v to get displacement, and I have a function for displacement as well, right? So you can, dx by dt. So then the x comes up here, t goes there, and I have displacement and a time function, right? But this is it. So this is the main idea. I wanted you to see that, and that's why I brought it out to the very end of this section, or the very end of this advanced series, because you've got an appreciation for bearing acceleration. You know how the calculus is applied. You've seen simple harmonic motion relationship, and you're able to kind of marry that together and kind of get a better real world perspective and see how these problems can be solved. Okay, so that should be it. And if there's something else that comes up, I'll probably add another video, but otherwise, maybe not. But I think this topic is good. If there's another topic, you'll see an extra video, but otherwise, good luck.